Dear students, welcome to the online lecture series of Nuclear Physics 2. The topic of my today's lecture is beta decay. In this lecture, I will discuss the various aspects of beta decay. First, I will discuss the basic decay process and its various modes, and then next the energy spectrum of emitted electrons will be discussed and explained, and next I will discuss the beta decay puzzle and how that puzzle was solved by the discovery of neutrino, and next I will derive the relation for the energy release in beta decay. Okay, so let's start with the basic process. We know that a nucleus is made up of two particles, proton and neutrons. So when one of them is converted into another, in the first I will discuss if neutron is converted into proton and electron. Then this process is called negative beta decay. Here proton stays inside the nucleus and electrons comes out of it, and this process is allowed on the basis of charge conservation. And next is the beta positive decay, in which proton is converted into neutron and positron. Again, this is allowed by charge conservation, and apparently it looks like that it's not allowed on the basis of mass conservation, because we see that a light charge particle is a light charge particle which is proton. This is converted into a heavy particle. This actually happens due to the conversion of energy into mass. Some of the decay energy is converted into mass, and due to that mass it enables proton conversion into neutron. Okay, next is the electron capture. This is actually the inverse process of negative beta decay. Here one of the inner shell electrons, this inner shell electron is captured by proton, and this combined product stays inside the nucleus in the form of neutron. Okay, but these processes are not complete, and there is actually another particle needed in order to complete the process. Actually, I will discuss why we need another particle for the complete description of these processes. So I will discuss in the coming slides. Okay, so first we analyze the energy spectrum of the electrons which are coming out of the nucleus. So we see that there are electrons with the varying energies. Okay, and there are many electrons which comes out with the smaller energies, and only there are few electrons which are coming with the maximum energy. So the question is, if electrons are coming with the smaller energies, then where is the missing energy going? So this was a puzzle in the nuclear physics for very long time, and it was solved later on, and in the next slide I discuss that. Okay, so if we compare this beta decay process with the alpha decay, then alpha decay is actually a two-body problem. where we have alpha particle and that daughter nucleus. So if we consider beta decay on the same footing, I mean as a two-body process, then we expect beta particles emitted with the well-defined energies. Or we can say that beta particles coming out with the mono energies. But in reality, beta particles are not coming with the well-defined energies, but they are coming with the varying energies. So this puzzle was solved by Pauli in 1931, who proposed that this beta decay process is actually a three-body process in which we have electron or positron and neutrino or antineutrino and the daughter nucleus. And the reason why neutrino could not be detected is due to its high penetrating nature, and it makes these particles their detection very difficult. So if we consider this process as a three-body process, then let's see how we can solve this spectrum of emitted electrons. So first I consider the beta negative decay. In beta negative decay, one of the neutron is converted into protons. That is why the number of protons increases and number of neutrons decreases, and we are having electrons coming out and neutrino. These neutrinos have certain properties. These are electrically neutral, and their mass is almost same as the mass of their mass is negligibly zero, and for the practical purposes we can consider the mass of neutrino as zero. So in order to find the energy released, what we do, we take the energy difference between the product and the initial between the product and the initial nucleus times the c square. It gives the energy coming out during this process. Okay, so but here if I want to convert the nuclear masses into neutral atomic masses, because it's convenient, and the tables are given for the neutral atomic masses, that is why I convert these masses into nuclear masses into atomic masses. So using this relation, we convert the this is a relation between atomic and nuclear masses. This is the nuclear mass plus the masses of electrons minus the binding energy. The reason why we are subtracting this binding energy term, because due to this binding energy the overall mass of the atom decreases. Okay, so by writing this equation number 2 in terms of atomic masses, we finally we have this relation for the energy released. Here I have collected the binding energy terms at the end. Okay, and we can see that the number of electrons are actually same here, and they are cancelling out. And the binding energy terms, the binding energy of the daughter of the parent and the daughter nucleus, this is actually the binding energy of electrons in the parent and daughter nucleus, and their binding energies are almost same, and we can neglect the difference in the binding energies. Okay, so by neglecting these binding energy terms and also the cancelling out these electronic masses, finally we reach at at the relation for the energy release. Okay, here. Okay. Now this energy, released energy, is shared between the electron and neutrino. Okay, and if we say that the maximum energy is carried by electron, then the neutrino will come out with almost zero energy, or if neutron is coming out with the maximum energy, then electron will be coming with the almost zero energy. And in other words, the maximum energy of one of them will be equal to the total released energy in this process. Okay. Now, considering the case of bismuth decaying into polonium, which was actually the spectrum I showed earlier was for bismuth 210, and now let's see can our consideration of neutrino solve the puzzle of beta decay. So writing the masses of bismuth and polonium and taking the difference, multiplying by this C square, so finally we get this 1.161 mega electron volt energy. And this energy, this 1.16 MeV energy, is exactly the same as the maximum energy of electrons coming out in the bismuth decay and in the spectrum I showed earlier. So this actually confirms that there is a missing, there is a particle which was missed earlier, and it was included by Pauli, and that inclusion led to the solution of beta decay puzzle. Okay, and we can work out the similar energy release relation for the beta positive decay. Beta positive decay equation is written like this, and by solving the similar equations, the same steps which I did in this slide and in the previous slide, we will reach finally to this result. This is the energy released in the beta positive decay. So I am leaving this step for the students to work out. There are few mathematical steps, and they will arrive at this relation. So I hope that this lecture will enlighten the knowledge of the students about beta decay and how discovery of neutrino and antineutrino led to solve the beta decay puzzle. Okay, thank you for watching.